Hey guys, Dr. Man is here yet again. Hey, it's one more time talking about kinetics. We still have a couple more to go after this one, but right now we're just talking about order. Order, remember, is the dependency of the rate on the concentration of a reactant. There's a couple ways to get it. It's always from the experiment. This is way number two. The last one was mechanism. This is from a ratio of initial rate data. Right? If you look at the table that's staring at you in the face there, it doesn't look like a mechanism. It looks like a table of data. And if you notice in one little spot, it says magic words of initial rate. How do you know it's initial rate data? Because it's a table with initial rates. Okay, I can't make it easier than that. All right. What you need to do is just compare how the rate changes with the concentration of the reactant. It's kind of like what we did a couple of videos ago when we described order in the first place. What you got to say is, look, man, from experiment one to experiment two, the rate's changing. Cool. If you look at that, you see that this is constant. So this change in the rate here has to be due to this change in the concentration of ammonia. That's what we're getting at. But realistically, you're probably not going to think of it that way. You're going to think, I need to get the concentration, the order of CO2. So I want to look at CO2's column, this column right here. I'm looking at that column. If I'm looking there and I say, hey, when is CO2 changing? CO2 changes from either the first to the second or the second to the third. Okay? If you look at that, from the second to the third, that's when NH3 is constant. So this change in rate here is due to CO2. So I want you to go back and look at me and say, look, as CO2 goes from 2 to 3, CO2 doubles. If you look at the initial rate data, the rate data goes up by a lot more. I don't know what that is. I do know what that is. I'm just joking. If the order was 0, no change. First order, same change. Second order is a bigger change. So if you look at that, you'd say that is not a no change. It's not a doubling. Okay, it's more than a doubling. So that's a big change. So you think that's second order. But realistically, this is a factor of 4. Okay, so the concentration is doubled. The rate goes up by a factor of 4. That's second order. It looks like it's the 2 times thing squared. So that's where the second order comes in. So we would say that the order of CO2 is second. And that's kind of like what I said right down here. For CO2, we're going to compare those two experiments. Okay. Concentration of CO2 doubles. The rate is 2 to the second, so that's second order. Now, bear with me, and let's look at ammonia. Ammonia, the second column, the NH3, ammonia, we want to compare these two lines because carbon dioxide here is constant. So this increase in rate, which looks like a doubling, 1.2 to 2.4. If you have trouble with that, just call it 12 to 24, man. It's easier. 1.2 to 2.4, it goes up by a factor of 2, which is the same thing that's going on over here as we go from a nickel to a dime. It goes up by a factor of 2. So we're seeing the same change. And so for ammonia, it's factor of 2, rate goes the same, it's the same change. That's first order. So if ammonia is first order, CO2 is second order, we would just write that groovy little rate law right like that. Okay, that's a short way to do it, but you need to know a long way to do it. And I'm going to do the same comparisons. And in CO2, we compared row 3 to row 2. And for ammonia, we compared 2 to 1. And what we're doing here is a ratio of initial rates. The rate laws, that is. Rate law is rate equals K, concentration, concentration. So we basically wrote the rate laws as a ratio. We did it here. We did it there for ammonia. Now, if you look at our rate law, since we're comparing 3 to, and we just plugged in the data, the same data that we were talking about up here, except like for CO2, we're comparing these two lines, concentration of CO2, concentration of ammonia, and rate, and we just sub it into our equations. For ammonia, we're comparing the other two lines, and we just sub it in. And then you do the math solving for the exponent. You may think, hey man, in CO2, there are two unknowns. I don't know M, and I don't know N. Well, hang tight, man. It's cool. Remember how one of them was constant. NH3 isn't changing. So if you look down here, it's going to cancel. Cool. And that's what's good about it. Just like before, we ignored ammonia because it was constant. We're ignoring it here, it's constant. And so basically, if you simplify the left side, you get 4. Simplify the right side, we get 2 to the m. What 4 equals 2 to the m? If you have trouble solving that algebra, it's okay. Make it multiple choice. M is going to be 0, 1, or 2. Which number solves the equation? It's got to, okay? 4 equals 2 to the m. What's the m? 2, because 2 squared is 4. Over here for ammonia, up here, carbon dioxide was constant, so it's canceling out. And we solve the left-hand side, get 2. Zero point 0.1 divided by 0.5 is 2, so it's 2 to the n. 2 equals 2 to the n. Again, n is going to be 0, 1, or 2. So which number is it? It's got to be 1. So there we have our orders, and we just write the rate law. Okay, so why would you write all that stuff out the long way? Well, if you want to justify something in a free response problem, it's a good way to justify it. But if your professor, aka me, would like to just make life difficult for you and see if you know what's going on, here's another example. Let's compare. We have initial rate data. It says so right there. Okay, so if we look at our concentrations, B is constant in 1 through 2. So if we look at A, that's a factor of 3. And I can't really do that. Looks like, oh, because there's exponents here. So it looks like that's going to be a factor of 3 as well. So it looks like it's first order. But get out of that for a second and go back to B. When is A constant? Because A is never freaking constant. So you're just done. All right, how are you going to solve that? You solve it by saying, look, for A, I'm going to compare experiment 1 to experiment 2. And that's what we're doing right here. Comparing 2 to 1. I put 2 on top so we'd have easier numbers. For order for B, I just need one where B's changing. I can compare 3 to 2 or 3 to 1. I think I chose 3 to 2. Okay. Again, I just substituted in the values. You might not know exactly where you're going, but you have a process. Write a ratio of rate laws, sub in the values, see where it takes you. Okay. And the order for A, B is constant, so we're canceling that. And you get right here, 3 equals 3 to the m. Again, m is 0, 1, or 2. Looks like m is going to be 1. Cool. Over here, where we had 2 unknowns, there's no way to solve it. M is no longer an unknown. So we can substitute it in there. And that takes us down to this line here. Now we only have one unknown n. We might have to combine terms like this factor of 2 here, because 1.5 divided by 0.75 is 2. We're going to have to move that over to the other side. But once we do that algebra, we're going to have this line here, 4 equals 2 to the n. N is 0, 1, or 2. That's going to be 2 squared. 2 equals n. Please don't be thinking it's 4 divided by 2. It's an exponent here, not multiplication. Okay? So it's either going to be 4 equals 2 to the 0th, to the first, or 2 squared. So n is definitely 2. Okay, so then we can write our group of the rate law. K equals to the first, B to the second. So that is ratio of initial rates. You just write in ratios, plug in numbers, and go. They can become more complicated. They might ask you for the value of the rate constant. If that's the case, you have a whole bunch of values in the table. You just pick a line, plug in the values of the rate, concentrations, solve for K. Hope you had a good time with this. Learn it, love it, like it. Talk to you later.